Yeah, welcome viewers. Today we want to be doing the analysis of statically determinate frames, and we want to take on some illustrative examples. This is going to be in a series. We're starting with this as an illustrative example. Now we want to calculate the bending moment, the shear force diagram, and the normal force diagram, and also draw this diagram. All right. So we have this frame on the board. It has one of its member to be slanted, and we have horizontal load of 10 kilonewton per meter and vertical loads of 30 kilonewton. We have the support. We have the pin support and the roller support. All right. So now let's go over and do the determination of the support reaction of this frame. Now, in doing the support reaction of this frame, we'll draw the free body diagram of this. Before we do that, let's label it. We call this A. Let's call this B. Let's call this C. Let's call this D. Let's call this E. So we have succeeded in labeling it. The next thing we are going to do is to draw the free body diagram of this frame. Now, of course, we know we have here to be pin support. So if this is a pin support, we are going to have a reaction, a vertical reaction. Let's call it VA. Okay. Here we are going to have a horizontal reaction. Let's call it HA. Okay. And at this point here, we're just going to have a vertical reaction. Let's call it VB. Okay. Now we have done that. So these are the reactions of this support. So the next thing we are going to do is to take moment about any point so that we can determine the unknown VA and VB. Now, but before we take moment about a point, let's get the equilibrium equation of the vertical forces. So we can say that sigma f of y is equal to 0. All right, f of y is equal to 0, meaning the algebraic sum of all the vertical forces to be 0. And in doing that, we assume the forces coming down negative, the ones going up positive. So we are going to have VA plus VB. We are going to have minus 30 times the span occupied by this UDL is 14 meters. So we're going to have times 14. Okay, so if we work this out carefully, we're going to have this to be 14. So we're going to have this. To work it out carefully, we're going to have this to be 420 kilonewton. Okay, so this is what we have as our value. Sorry. So if we work this out, this equal to what? 0, meaning that VA plus VB is equal to 420 kilonewton. This is our equation 1. Okay. So having gotten this, the next thing we want to do is to obtain one of these unknown, either VA or VB. Now let's start with VA. Now taking moment about point B, what we are going to have, if we take moment about point B, this you are going to have this moment is going to be clockwise. VA reaction VA will produce a clockwise moment. The uniformly distributed load will produce an anti-clockwise moment about B, and also the uniformly distributed load here will also produce an anti-clockwise moment about B. Okay, so this is how we note them. Now we equally have a reaction HA. HA is already at the same horizontal line as B, so it's not going to participate in this process. Now, the first thing we will do, let's obtain the let's take moment about point B. So we'll say algebraic sum of moment about point B, let it be 0. Now the Clockwise moments are assumed to be positive, anti-clockwise moments are assumed to be negative. So if we do that, we will have VA times the, the reaction times the perpendicular distance of the point of action of the force. This is VA, this is our point B. So taking moment about point B will give us VA times B. So VA is positive times perpendicular distance to B, which is 14. Okay, so that is positive. Now we have the next one, which is 30. This one is anti-clockwise, so it's going to be negative. So we have 30 times, the span here is 14, so 14 times 14 over 2. So that is what we have. And the last of them is this. We're going to have this moment about this point. It's an anti-clockwise moment, so it's negative. So it becomes 10 times. The height here is 5, so it becomes 5. The span is 5, so it becomes 5 squared over 2. So this is what we have. So we'll now have equal to what? Equal to 0. So we now have 14 VA is equal to, let's work it out. This is 7. Let's see what we're going to have. So when we work this, all right, so we have 30 times 14 times 14 times 0.5. So this is 2,000 plus 10 times 10, so 10 times 5 times 5 times 0.5. Okay, 3065. So when we work it out, we are going to have it to be 3065. All right, so we have our VA to be 3065 over what? Over 14. So if we do that, we're going to have this divided by 14. That will give us 218, 218.928 kilonewton. Okay, so this is what we have as the VA. So this is our VA. Have our VA. Now, having gotten VA, what we need to do is to obtain our VB. Okay, so we know that our VB from equation 1, VB will be 420 minus 218.928. So if we work that out, minus 420. So that will give us 201. So this gives us 201.07 kilonewton. Okay, so 201.7 kilonewton. This is what we have for this particular work. Now, the next we are going to work on is the summation of all the horizontal forces. So let's say sigma f of x equal to 0. That is the algebraic sum of all the horizontal forces. So we have, let's assume the horizontal forces moving towards the left, towards the right hand side to be positive, while those moving on the left hand side to be negative. So this one is positive, this one is coming negative. So we have it as HA positive minus 10 times 5. Okay, this gives you 0. So we can now say that HA is 50 kilonewton. All right. So if HA is 15 kilonewton, that gives us the value for the horizontal reaction. Now, having gotten HA, the next thing we are going to do is to start obtaining the bending moment of this particular frame. Now, in doing that, the first thing we will need to do is to split the frame into three components. We have this as a component, we have this. So we are going to split it into three components. Now, take note that from here to this point, from here to here is 4 meters, where we have a cantilever of about 4 meters. So of course we know that the bending moment, the moment at the support of the cantilever is going to be the value of the uniformly distributed load times d square over 2, which is WL square over 2. So, but before I do that, let's split the beam into its component. So splitting this beam, we are going to have it as this. There's the first one. We're going to have it as this. So now there's a vertical reaction here. If we split this, we're going to have this beam. At this point, we have the support here. It continues. At this point, we have another support. Now, take note, the vertical reaction here will be an axial force running through to this point. So the reaction here becomes the reaction here. So when we split, we're going to have it as this. We have a reaction. Let's call it this will come down. Okay. So the value of, we have a reaction going this way, which is reaction. You can call it a reaction going this way. This is VC, and another one coming down, which is VC. So if you split this part of the structure, you are going to have it as this. You will see them. This is this reaction VC. This one is VB. This one coming here will be VC. All right. So we can say that VC and VB are equal and opposite in direction. So since they are equal and opposite in direction, it means if VB is 201.07, VC will equally be 201.07, because why? They are equal and opposite in direction. So what it means is that at this support here, we're going to have our VB, which is then as our VC, and the value is 201.07. All right. Now the next one we're going to look at is this. Now, if you split this, remove this part of the support from this beam, you will have it as this. You see it like this. So the support reaction is here, where you split it. Now, when you split it, there's going to be another reaction coming down. All right. Another reaction coming down. Why another one going up to carry this? So we're going to have two reaction, one coming down here to pick this beam, while another one going up here to support this horizontal beam. Okay, so you're going to have it as this. Remember, here is we have here to be HA. So whatever value we have as support reaction here will be the same as the value we have as the reaction for this beam. And also, whatever value we have as a reaction here will be the same as the value here, because if you do the algebraic summation of vertical force here, you see that this reaction is the same as this. So we've already gotten this before to be 218.928. So we've gotten that before, so we may not need to work on that. So what it means is here becomes 2. It becomes 218.92, 28 kilonewtons. So this is the first part of the beam. Now the second part of it, now what we'll split it, of course we know there's going to be a moment here at the support here. All right, so we're going to have a moment here. We don't know the value yet, but there's going to be a moment there. Now when we split this beam, it comes like this. Once this moment here is a clockwise moment, we'll have the same value for moment on this side of the column of the same magnitude. Okay, now you also have the reaction coming down also, while here you have the reaction going up. Here you already have horizontal reaction. The horizontal reaction, you have it to be 50. So here is 50 kilonewton. Here is 218.92. Okay, we have a moment here. Let's call this moment DA, moment DA. Okay, whatever we have for DA will be the same as moment DC. Let's call this one moment DC. DC. So whatever we have for DA is what we'll also have for DC. Okay, we have a moment MDC coming this way, another moment MDA. So both of them are of the same magnitude. But all right, so like I said, we're going to have a clockwise moment at this direction. Let's call that moment MDA, and let's call the one due to DC to be MDC. So this one is moving clockwise, this is going anti-clockwise. So when you bring it together, they become neutral. Okay. Similarly, we have a moment at this point, which will give us 80 and WS squared over 80. So we have that. Now let's redraw this structure, and let's take our moment and obtain the unknown. The only unknown we have here as it stands, we have MDC and MDA. We don't know their value. We need to find out what they are. Now, looking at it, let's pick it separately. Let's pick span AD. AD. Let's pick this AD. So pick AD. I'll find out the moment at D due to AC and the moment at D due to DC. So they are going to be different moments. Okay, so let's find out what the value for the moment are. Okay, so let's find out what the value for the moment are. Now in doing that, so we have a moment here. We call this one moment due to DC, while this is moment due to DA. So we're going to look for this moment. Once we have this moment, we can be rest assured that we're in good form. All right, so let's go. I'm going to redraw it. I'll pick A to D. This A to D. Let's pick it for to D. We'll have it as this. We have here to be 218.92. We have this span to be 4 meters to this point. We have this is A, this is D. At this point, we have a moment. So we have a moment here, which we are going to find out. And we know that the reaction coming here will be equal as 1.892. Okay, so let's treat this first. Now, in doing this, we have also, so we need the moment at D, moment at D due to moment dA of moment about point D to be 0. So it means this one, this is a moment, this is a clockwise moment. So we're going to have 218.92 times the moment times the perpendicular distance to D, which is 4 meters. So this becomes times 4. Positive moment because it's clockwise. Now we have this, which is 50. Now 50 is going to be moving to D. 50 will be moving in an anti-clockwise direction. This is the direction of the force. This is the perpendicular distance. Remember that this distance we have here to be 5. So if here is 5, remember that from here is 5 meters. Okay, so we have it to be 5 meters. So this force acting is going to be acting somewhere around here, and it's going to be causing an anti-clockwise moment. So this force is causing an anti-clockwise moment about D. So an anti-clockwise moment would assign it to be negative, so it becomes 50 times 5. Okay. Now we have at D a moment which we call dA. So that one is anti-clockwise. So we'll just say MdA, all equal to 0. So if we do that, we are going to say that MdA becomes so MdA becomes 625.68 kilonewton meters. That is our MdA. So once we know MdA, the next we're going to consider the next span. We're going to be considering this time. Okay. So what do we do? Now, if our DC is equal to our DC is equal to our MdA, what it means is, in getting the moment here, we're going to have the moment expression as this. M of x is equal to the UDL here is 30, so we have minus 30 x squared over 2. Then we'll have plus 218.92 x. Then we'll have plus this MD. We'll have MD to be what? This is it. Now, this is our reaction. We have our reaction at this point. Now, from here down the 0 mark to here is x. So we have is x. So from here it's 4 meters. So here becomes x minus 4. Okay, that becomes x minus 4. So if we write the moment expression, we'll have m of x to be m of x equal to minus 30 x squared over 2. Then we'll have plus 218.92 x minus 4. All right. Then we'll have a moment. Remember, we have a moment we call MDC. MDC is of equal value with MdA. All right, under equilibrium. So we're going to have MDC, our positive MDC. Okay, so that gives us the expression. So if we continue in this format, we're going to have m of x is equal to minus 30x squared over 2 plus 218.92 x minus 4 plus MDC, we got it, is the same thing as our MdA here. So we have it as 625.68. So we have it as 625.68. Okay. So we have it as 625.68. So if we come this way, we can so if we come this way, let's look at this. Let's write it here. So we have it as m of x, where x is equal to 4, will now be minus 30 times 4 square over 2. Then we'll have plus 218.92 times 4. 4 minus 4. All right. Then we'll have plus 625.86 plus 625.86. So this will have, so m of x when x is equals to 4 will give us, this will cancel out, become 0. So that will give us 385.56 kilonewton meter. So this becomes the moment at this point D due to member DC. All right, so this will have for that moment. So now I haven't gotten the moment at every edge of the frame. We are going to draw the bending moment diagram. Now let's consider this UDL. Between point D to C, we are going to look for the maximum moment at that point. Okay, so let's look for the maximum moment. The maximum moment will occur at the point where we have 0 shear force. Now the shear force expression for this particular beam, let's see if we can get that done. With this space, let's obtain the shear force expression. So we can have the shear force expression as equal to minus 30x, all right, plus 218.92. Okay, so this is equal to 0. So we'll have x is equals to 218.92 over 30. So let's do that. When we do that, we'll have the value. All right, so dividing it by 30 will give us 7.29 meters. So that is the point of maximum moment. So in determining the maximum moment between span DC, we can come and say maximum moment between span DC, the maximum moment between, can say that the maximum moment between span DC, we can say M maximum is when S is equal to 7.92 meters, and that is, substituting it into this expression, we'll have 30 times 7.29, so we'll have here to be 7.29, so this is 7.29, so become 3.29. Okay, so when we do that, we're going to have the maximum span moment. Let's work it out and find out what we have as the maximum span moment. So like you can see on the board, we've been able to calculate the maximum moment in span DC, and that gives us, I will multiply 30 by 7.2. plus this moment. This gives us 548.94 kilonewton meters. All right. So this is the maximum moment across along span DC. So with this moment, we can draw the bending moment diagram with the very ease. So we can go ahead. Let's do that. And for moment, initially it was 240 kilonewton meter, negative 240 kilometer, and the direction we assume for that cantilever was uh, assumed to be uh, anti-clockwise direction. Okay, cantilever. So once we know that the cantilever has negative moment and the value for the moment is 240, and also for these other beams, for example, the slant side, we have the moment to be 625.68. It means that we have the other one. It means that this, if this is a negative moment, it means by the time we do the algebraic sum of MDA, moment MDA, remember that MDA was 625.68. Remember that MDC was, we have MDC, which is when S is 4, as 385.56. Remember, this is the moment we have, okay? MDA and MDC. So MDA and MDC. So by the time we take the algebraic sum of this, it must be a positive value. So if it must be a positive value, it means this will be positive and this will be negative. All right. So if this is negative on this direction, it means we're going to have a negative moment. If it's going to be negative, it means it's going to be coming down. It means it's turning in anti-clockwise direction, so it's going to be coming down. So we'll have it coming down here, and it goes, follow the curve until it gets here. Okay, so this is how we'll have it. Because this is a negative moment, it must be a negative moment to balance up what we have here. So it's going to come down. Now the next one we are going to see is this one, which is 63. This one will come. So we'll come this way, then okay. So you can see that this one is pushing this down below. This one is having a hugging moment at that point, a negative moment at that point. So now we have here to be 625.8, 625.68, okay, 0.68 kilonewton meter. Why here we have here to be 385.86 kilonewton meter. Okay, so once we have this, right here we have here to be 125 kilonewton meter. We have the other side of it to be 125 kilonewton meter also. So we can shade it off. If you wish, you can shade it off. So this becomes the bending moment diagram for this frame. All right. So I believe with what we have done, we can be able to do problems on bending moment diagram and shear force. So we're going to continue from here in our next lecture. In our next lecture, we're going to treat the determination of the shear force diagram and also the determination of the axial force diagram. So thank you very much for watching. I believe you do enjoy the lectures. But if you do enjoy the lectures, I want to say do well to subscribe to our channel. To be seeing you in our next lecture. Stay well and stay cool.